Yeah, I'm Rob Bond. I'm a technologist at Temporal, as Jessica has said. Recently, one of my many roles has been working on benchmarking Temporal. And kind of out of that, I've had to drag myself up such that I understand like how to get better performance out of Temporal, so I can help users like Mackie, I see here. Hey. And so I want to sort of present a very brief, unfortunately, because I only have 30 minutes and I could literally stand here all night to talk about this stuff, sort of intro into what I've learned and hopefully give you like jumping off points to improve your sort of testing experience with Temporal and sort of how you can go to the next level, scaling Temporal up on self-hosted. I will just say, like 90% of this talk is focused on self-hosted Temporal. There's a lot you can do to tune your workers when you're using Temporal Cloud, but most of this talk is to do with sort of hosting it yourself. So a bit of what we're going to do. There are some like resources associated with this talk for you to sort of dig in on your own later. So everyone's favorite, there's a QR code here. Sorry, I keep talking where the mic isn't. I do apologize. I'll try and be better at that. So bring that up. I will actually be probably quite painfully switching to a tab with that to sort of refer to during my talk, but I'll try and keep that to a minimum. So agenda, I'm going to talk about why you'd want to test performance. There will be some obvious reasons, but some perhaps less obvious, so I'll go through that quickly. Going to give an overview of what sort of the setup looks like when you're trying to test Temporal. Talk about load generation, so how you actually introduce load into the system to sort of observe the behavior. Measurements, so there's a couple of different kinds there, which we'll go into. Sort of, basically, what are you looking at? So how do you define success and that kind of thing? And I'll give you examples of specific metrics. Also, big shout out to Datadog. They've just produced like a dashboard integration as well, which hopefully will sort of present these things like really in your face and make it a lot easier going forward. So if you're a Datadog user, definitely use that. And then at the end, obviously, there'll be a summary and we'll go over sort of some key takeaways to hopefully sort of help things stick in your mind and think about what to look at when you get home or back to the office. So why test performance? These slides I wrote. Don't blame anyone else. I'm so sorry. The emojis are awesome. So a lot of it comes down to planning and some particular reasons for that as well, including the big sort of elephant in the room, which is when you build a cluster, you have to pick something called the shard count. And we'll go into the details of that in a bit, but you can't change it after the fact. So capacity planning is a big one. You need to make sure when you build a cluster that it's going to have the capacity to hold your production traffic at the throughput level that you want it. So that's really important. That's why I'm a big advocate of performance testing and sort of experimenting with Temporal yourself. Making sure that whatever database engine you'd prefer to use can be pushed as hard as you need it to be. And we'll talk about that later as well. So basically it's scaling future-proofing. You can be going the opposite way. You can have a really awesome sort of production system and you're thinking, well, we're self-hosting. Maybe there's a way that we could be sort of running this more optimally and more efficiently to sort of reduce the cost of the self-hosted Temporal cluster that we have. So that's another reason you might be performance testing. And then the sort of experiments with, my application is sensitive to this specific thing. How realistic is it for me to sort of drop this metric and sort of reduce this so that my application gets a better experience? Testing infrastructure changes, so you might be sort of testing the ratio of different services to each other or something like that, and then sort of testing changes to your workflow architecture. So there are locks in Temporal and that kind of thing which are sensitive to the way that specific workflows are designed. For example, it's not a good idea to have thousands and thousands of signals going to a single workflow, and there's other kind of other issues like that can affect performance. So you may be thinking, okay, I'll take my production code and I'll tweak it and then I'll performance test it and see the implications of the changes and make sure that they're moving us in a positive direction before sort of rolling this thing out and it all going horribly wrong. So we're going to look at what performance test system looks like with Temporal. I'm going to start on the left. Anything that's grayed out in any of these slides, you don't worry about it. Like we'll come to it later, so don't stress. You're going to need a performance test application. So this is like depending on the reasons for your performance testing. I should just stop here and say, like there's two primary ways of performance testing Temporal. One is I have this workload, like my company needs to run these workloads, and I need a cluster to sort of push this specific workload to a certain point. You have your goals for maybe latency or a number of workflows started per second, or whatever your requirements are. So you might be bringing your own workers because they'll have your workflows, specific to your workload, and you may be sort of mocking out the responses or whatever, but it is your code. So you're bringing your own SDK language or whatever you're using. There is another way, which I'll also sort of cover as we get through this stuff of testing Temporal, which is more how hard can the internals of Temporal be pushed on a cluster of this size. And what I mean by that is all of the sort of value that Temporal adds to you basically hangs off the fact that we're persisting stuff to the database all the time, so that if something goes wrong, we can carry on where you left off. And so there's like a core metric which measures how much work we can do for you. And so for that reason, you might want to be pushing Temporal like harder than you would in your workflow in terms of number of operations that Temporal has to do per second. But you can then relate that to your workflow afterwards. So it's like an abstract way of testing Temporal, if you like. How hard can I push this cluster? Like, I'm going to be really mean to Temporal and throw loads of stuff at it. So it has to do like a lot of work for every workflow. And we can get a number out of that to say, okay, this is how hard this cluster can be pushed. So we've got your performance test application. It may be based on your application code, or it may be this abstract stuff. These really simple but painful workflows for Temporal in a deliberate way. So your worker is going to be at the bottom. They're going to be polling and executing. That's what workers do. And then you're going to have some kind of load generator. So given that the sort of top level primitive in Temporal is a workflow, you can't call interactivities directly at the moment. You're going to be starting workflows, basically. That's going to be how you can generate your load. So that's the left-hand side here. And then you're going to need a Temporal server. We're not talking about cloud, as I've mentioned. So you're going to have to be self-hosting. And these are the sort of components that make up a Temporal system. Because of the timescales of the talk, I only have 30 minutes, for which you'll probably be very glad. But these are the. I'm going to assume that you've deployed Temporal before. If you haven't, this is going to be a bit rough, maybe. But we'll do our best. But you can always refer back to the slides and stuff. But this is what a Temporal server self-deployment looks like. So I'm going to go through the services just quickly. So on the left, you've got the front end, and that's where all the gRPC connections from the worker are going to land. And the front end is going to hand off to the relevant service further down the line, depending on what you're asking it to do. So we've got the history service at the top, and the history service is responsible for sort of looking after all the state that the workers are producing. So that's where the event recording magic happens, and that's what allows us to sort of resume where things crashed if we need to. And then the matching service, which is responsible for sort of matching up, funnily enough, the workers who are polling for work with tasks that Temporal has decided are available for those workers to do. Internal worker on the top right is grayed out. We don't really need to talk about that in a scaling point of view because it scales so easily. It's very obvious how to scale it. You just add more processes. There's nothing else to it. And also it tends to use very little CPU, so it's not really interesting from a scaling point of view. And then the bottom here, we've got persistence, which is what we actually persist everything to. So that'd be kind of CDS in the according to Paul's talk earlier. But normally when you're self-hosting, you'll be directly connecting to Cassandra or MySQL or Postgres or whatever, or in case of Temporal-Lite, SQLite. And so this is your database engine, basically, sort of underpinning the persistence aspect of Temporal. One thing that I need to mention, which is really important, is that if you're performance testing Temporal, it has to be repeatable because you will get different results every time. How different will depend on a lot of things, but like the sort of general direction of your tests will be consistent, but you will get different numbers every time. So everything needs to be ideally defined by some kind of config file or a script or some kind of harness where you run a test, it spins everything up, it runs the test, it spins everything down again. And you need to be able to do that repeatedly. Don't sort of make manual changes because you'll forget to repeat them and that kind of stuff. So a big theme of all of this is always rerun your tests. And this is sort of, to some extent, general benchmarking practice. In science, you wouldn't just run an experiment once, but I just want to make sure, don't get into the trap of manually doing stuff and then realizing that you need to run it again. And you can't actually remember how you configured your workers. Try and make everything repeatable. That goes for the cluster as well, particularly because to get a fair test, you need to destroy the persistence database between runs or wipe it, whichever is easiest for you. So make sure that that always happens and you can't accidentally forget to do it between tests because there's a very simple example. Most of the workflow tools you use will probably start at deterministic workflow ID, so they'll probably start at 0. Now, if your database already has workflows with those IDs in it, you'll get errors, even though, in a new run, you'd not get errors because it would be able to start the workflow. So it's just stuff like that. You need to make sure that everything is scrapped every time and then built up fresh. Always repeat the tests. Always use a tool or a script. Terraform or Pulumi are very useful because they allow you to build the infrastructure and aim for a single config file. Now, this is going to be jarring. Sorry about this, but I'm going to try and switch. Oh, wow. OK, that was not as painful as I expected. So this is where the QR code link will take you to this page. So I want to show you some examples of, just quickly, of tools that we've used. We've got a repo called the benchmark matrix. This is where my benchmarking code lives. It's all open source. You can mess around with it, file bugs and all that good stuff. So that's a tool based on Pulumi. You probably can't read it particularly well on the screen, but just so you have a sort of feel for what it looks like. At the moment, it only creates AWS infrastructure. So what it will do is it will spin up a new EKS cluster, start Temporal, migrate the database, all that stuff. And then fire up some workers to sort of handle the load and then start the load test. So that's already available for you to look at, even if you just want to sort of figure out how we're doing it. And then to the point about the config file, again, I don't know how. Okay, I was trying to zoom in there, but I can't easily do that. Basically, the config file here controls everything about the test. So it defines how many nodes the EKS cluster has, what the instance types are. It tells us what MySQL instance we're using in this case, but it could be Cassandra or Postgres or whatever. And then it's the number of pods we're using for each of the various temporal services, number of workers. There's dynamic config at the bottom here. I'll get into sort of what you do with that a bit later. But this means that if I sort of input this file to the test system, I'll get the same test every time. I won't get the same results for the reasons I mentioned before, but I'll get the same test. And it means that I can sort of make changes here, rerun the test, and check that I'm moving in the right direction. Can I get back? Are we feeling lucky? I cannot get back. Thank you. This is Lauren. He's fantastic. We love Lauren. Okay. Thank you. So, and then I want to talk a little bit about methodology. I mean, again, this is kind of scientific rigor in some ways, but specifically to this, like Theo was saying with his stack bookcases in his previous talk, if you caught that. So the kind of process methodology that I think about when doing this kind of stuff is you're going to add some load to the system. So you're going to create some workflows. You're going to measure, so you can look at your instrumentation and you can see what's going on, if you can see any bottlenecks or anything that you need to react to. You're going to scale out to sort of compensate for whatever bottlenecks you're seeing. And then you're going to measure again, and that's kind of a cycle. So it's going to look most of the time like this. You're going to add some load, either your intended load or you're just going to sort of work load up slowly so that it's easier to spot the bottlenecks. And then you're just going to go into this loop of scaling things up and then retaking your measurements to make sure that you're not exhausting CPU on something that you weren't before because you've added more shards or anything like that. So that's the process. So let's talk about load generation. So just as your normal application would, the input here is workflows. You're going to start workflows. You want to do that in a controlled way. There's various ways to do this, but the basics are always going to be the same. You're going to be starting some workflows. Your worker's going to be polling for those, and then executing, and you're going to watch what happens. As we said, there's two ways to test. There's kind of specific to your workload, and there's abstract. Use your own workflows if you need to test your specific workload, obviously. And if you don't, there's tools that have generic built-in workers which are designed to push temporal in a really annoyingly hard way. So two of those are mentioned here. They also link to in the slide, which I won't now. Oh, thank you. I won't now sort of keep flicking to because it takes me too long. But a couple of things I want to mention. Benchmark workers is very simple. It just has a tiny workflow which just runs an activity 3 times, which is like a nice inflection point for temporal state transitions. And then OMES is slightly more complicated, so it can do things like scenarios. For steady state testing, which is what I would normally recommend, so this is where we take a cluster and we say, how much load can we add to this cluster and it still be within headroom? So give us sort of the room for spiking without actually getting into that sort of territory. Benchmark Workers is really great for that, and I'll go into why in a sec. I do want to mention back pressure. So what I mean by this is that you're going to start some workflows. Eventually, they're going to complete, particularly if you're in the abstract case. So you're testing, you're really thrashing temporal and seeing how hard you can push it. If you do like an Apache bench style stuff, I don't know if you used that back in the day, where you're like saying start 5 workflows per second or something. Well, no, let's not say 5, let's say 50, whatever. And then you don't actually check how many of those are completing. What you can do is when you have a bottleneck, you'll build up a big backlog. You'll make a change to the configuration to try and scale things out to better compensate with the load. And then it has to recover from the backlog before you see the effect of your change taking place, because it has to sort of recover from the spike first. So we can use like back pressure in this case. And all I mean by that is when you start a workflow, you wait for it to complete. And rather than using the number of workflows per second as the measure of sort of how hard you're pushing it, you instead use the number of concurrent clients that you're using to start workflows as the measure. So Benchmark Workers will take an argument and you can say, okay, I want you to create like 500, 1,000, however many clients, and it will create those clients concurrently. And all of those clients will start a workflow, wait for it to complete, and so on and so forth. Now, what this does is that it means that if you also have a bottleneck, those workflows will take a long time to complete, but that's fine. You'll see the sort of bottleneck in the instrumentation, and then you can tweak and scale out, and it will recover very quickly because then those workflows will complete, but you won't race ahead creating like a million more workflows. So it gives you a much easier way, a much quicker iteration time to see how you're doing and how your scaling is going. I am a bit behind time-wise, so I shall try and race through this. There's 2 kinds of measurements that you're going to be looking at. One is results, state transitions in this example, top left, and the others are more to do with SLO. So we saw Tiho's talk earlier about latencies. There are things that matter in terms of throughput for your application, and then there are sort of business requirements around how quickly Temporal responds to your application. I don't want to be sitting waiting for Temporal to say it's going to run this workflow for me for like 200 milliseconds or something. That's too slow. I'm just picking an arbitrary number, but you get the idea. So there's kind of like pass-fail for a benchmark, like this cluster is not okay. And then there's like, okay, this cluster is okay, but how far did it perform? So the state transitions is how well, how hard could I push it? And then the SLO stuff at the bottom, and I'll give some examples, is this, at this performance level, is this cluster okay for my business? Like, can I wait this long for the latencies? And you can use alerts to do that, as Theo did earlier as well. So we can see here, request latency. For my benchmarks, I always say 150 milliseconds for this particular latency, which is how quickly Temporal says, yes, I can run that workflow for you. Bear in mind, that's not Temporal starting the workflow. It responds as soon as it has successfully recorded the request to start the workflow. So this is like not bounded by how quickly we can start work, but it's just Temporal saying, yes, I've got that. I won't forget it. It's on my post-it note over here, and you can sort of get on with your day. So this will vary based on sort of business cases and stuff, but I set 150 milliseconds. You can see in this slide that that's failing, so benchmark is not okay. We need to scale and sort of get it into a better place. Performance metrics. Again, it depends whether you're testing a specific workload or abstractly. So state transitions is the one metric that I'm really going to talk about, which comes from the server side. The rest are all going to be SDK metrics. State transitions is a measure of how much work Temporal is doing to sort of give you the value that we give you. So all of the durable execution stuff is underpinned by the fact that we're recording stuff to disk, and state transitions is a metric which is emitted every time we persist something to disk. So it comes from the history service, and this is what you'd use if you're sort of trying to push a temporal cluster in like a really evil way to see how much it can cope with. And the other metrics I'm going to talk about all come from the SDK. So they're more related to how your application perceives its interactions with Temporal. So latencies, number of workflows started per second, completed per second, that kind of thing. So you can see some examples here. So one result metric might be, if you're like testing for a specific workload, the number of requests per second started. the number of start workflow requests per second that Temporal can acknowledge. So how quickly can you feed requests to Temporal? Then how quickly those requests are responded to is like an SLO kind of thing. Like, is it quick enough for my application to be able to get on with other work rather than waiting for Temporal all the time? And then there's stuff from the actual workers as well. So a number of workflows you're able to actually start work on per second, completed, end-to-end latency, that kind of thing. Again, because if you're testing abstractly, you don't care how many workflows you get through, you just care how much work Temporal had to do to service them. So these are only sort of relevant if you're testing a specific workload, but I wanted to mention them. SLO for sort of worker side stuff is scheduled to start. How long does it take between me requesting a workflow to start and it's actually starting? I mean, actually it's for workflow tasks, but it's still a measure of how up to speed your workers are with your workload. So scaling. Can I get to that? Thank you. Oh, wow. Okay. So we're going to run through this. Please catch me afterwards if you have any questions. I've managed to overrun. I'm sorry. So we're going to talk about scaling persistence. Not going to talk much about this, not because it's not fascinating, but because it's so varied between the different persistence engines that it's not worth going into. The gist of it is you're going to care about CPU. You're going to care about probably concurrent session count, so how many statements or transactions can be active on the database you're using, and disk I/O throttling. As Paul mentioned in his keynote, we're really write heavy because most of the time we're trying to sort of stuff into the database, but hopefully you're not going to have any crashes. So we don't really need to read it back most of the time. Everything's cached at various points. So we're really write heavy. It is almost always the case that you can get a temporal cluster to the point fairly easily that the persistence backend is the bottleneck. So definitely always keep an eye on your temporal persistence. Some things scale better than others. So SQL databases, for example, won't be able to be pushed as hard as Cassandra. As Paul said in his talk as well, even Cassandra has a limit, even though it does scale horizontally. There will be a point you can't push it hard enough, where you have to think about sort of implementing things like CDS. But Cassandra can go really big. It's more difficult to manage, so it's a trade-off. But if you have that in-house, then think about Cassandra as well when you're evaluating persistence backends. All of the temporal services, you need to be thinking about CPU percentage and CPU throttling. CPU throttling and CPU usage percentage are not the same thing. CPU throttling is sneaky. You must be checking for it specifically in your metrics. Use Datadog, Prometheus, whatever it is, but double check that you're not being throttled. I'll show an example of that in a sec. How do you fix things if a service is at its CPU limit or being throttled? Throttled specifically, there's a resource in my QR code thing that you saw that deals with it. I'm not going to go into it too much here. CPU percentage is fairly straightforward. You add a core to the process, like the history service or the matching process or whatever it is, or you add another process. Both are sort of ways to solve this problem. Normally you'd add processes rather than cores. We'll talk about balancing in a sec. Memory limits, with the exception of history, memory isn't normally a problem with temporal. Things will very consistently use the same amount of memory. You can watch them, you can set your limits, you can sort of get on with your life. RPS limits. The RPS limits that we set, which is limits between the number of requests that the various services can send to each other and also incoming from your code, are quite conservative. So you may find that you've got loads of CPU headroom when you hit the RPS limits. You can just bump them in dynamic config. Again, there's a reference to that in the resources thing at the end. So this is kind of like this is how all of the services scale at a very sort of wide view. Just want to call out CPU throttling. On the left-hand side of the timeline, you can see the red area on the CPU graph there. That's a process which is, although it's not even at 60% CPU, is throttling. Throttling is really bad for latency. You don't want throttling. So definitely read up if you don't understand what CPU throttling is and the impact it can have on the resource list I showed you, and that'll show you how to sort of improve that thing. I just want to call out as well, once we fix the CPU throttling, you can see the impact on the latency at the top. So the top left there is kind of spiky. It's, I wouldn't say all over the place, but it's not particularly stable. And then after we fix the throttling, not only does our CPU usage go down counterintuitively, but the latency is lower and more stable. So definitely look into that. Scaling front end. Scaling front end is quite easy. If it's using too much CPU, add a process. The only kind of thing to mention about this is RPS limits. Make sure that you're watching the metrics for RPS limits. They will let you know if something's being limited, and then you can make a decision as to whether you want to add another process or up the RPS limits if you have the CPU headroom. The only thing I'll say is when you add a process to front end, it won't immediately rebalance all of the connections because it uses gRPC connections from the workers. They're long-lived, they're multiplexed, or loads of requests are going to go over the same connection. It will eventually rebalance, but don't be scared if it doesn't quickly rebalance. Over time, the connections will balance across the new pods. Scaling history. So again, CPU usage. Memory on history is surprisingly high for some people because we keep a cache of event histories for the workflows. So you need to be careful that history processes don't run out of memory and get own killed or out of memory killed, because that's really bad for the performance of the cluster. So keep an eye on history memory. If it's using more than you're happy for it to use, you can adjust the cache sizes down in the dynamic config to sort of compensate for that. So it's kind of a trade-off between how much memory you're willing to give it. The sort of balancing primitive for history is history shards. So we split the entire workflow execution state universe into shards or partitions. And each history process that you create, so pods in Kubernetes, for example, will get a set of those shards that it's responsible for, and only that history pod will process any requests related to that workflow execution, or the workflow executions in that shard. The number of shards is not even because that's how Temporal works. The balancing will not be even across history processes. And the reason is, when you're adding and removing history processes during a deployment, we want to try and keep as many of the shards that were on a history process that's still up on that shard as many of the shards that were on that history pod as we can still on that pod. So we don't uniformly rebalance everything. We try and keep stuff still where we can. That means that we won't evenly balance across all the processes. You can see up to 2 times more shards on one pod versus another. So that's something to bear in mind in terms of history and CPU usage. You have to kind of aim for the highest loaded history pod. The usual shard range for production clusters is sort of 512 to 4,000. Shards are actually used to limit the concurrency of writes to the database because you can only write to one workflow execution per shard. This is due to a limitation in how Cassandra transactions work. We also apply that limitation to SQL databases, although we are planning in the future to lift that so that hopefully we can push the performance of SQL databases higher. At the moment, they still have that restriction. What this means is that the history is often a bottleneck because the number of shards literally is designed to limit the amount of concurrent writes we can push to persistence. And almost every interaction with Temporal involves writes to the history because that's our job. That's what we do. We manage history for you. And that's how we provide the features that we do. Don't just whack the shard count up really high because every shard has CPU, memory, and database sort of constraints to manage it. So it has a cost. So this is one of the reasons you should definitely test for performance a lot. Make sure that the shard count that you're using on your cluster is enough to cope with your traffic, but not too high because you're paying indirectly for that high shard count as well. Like I said, these are the usual shard count ranges. We do have shard counts that are higher, but it's unusual. Gone through that, I think. Okay. How do you know when you need more shards? Shard lock latency is the metric that you want to be watching. On the left, we can see shard lock latency is like 50 milliseconds. That means for every update we're trying to make to a workflow, so every time a workflow makes a bit of progress, we're trying to take a lock for the shard so that we're allowed to write to the database for that workflow execution. And it's taking us 50 milliseconds to get that lock. That's way too slow. You're going to bottleneck very easily on that. So at that point, we know we need to update the shard count. By the way, all of this is included in blog posts and stuff as well, which I linked to, so you can sort of drill into this more. I'm sorry I'm rushing through it so much. We update the shard count on this cluster, which means rebuilding it. Remember, we can't adjust it after the cluster is built. We have to blow away the entire persistence backend, recreate it with the new shard count. Shard lock latency is the green line on this graph here. You can see it's dropped to 1 millisecond. Now, I mean, that's pretty amazing from 50. We're really happy there. It's not an issue. One of the things I was saying about measure and scale in a loop is that you can see now on the top right, because we've upped the shard count, every history pod is now caching a lot more because it's responsible for a lot more shards. So you need to watch out for that kind of thing. And then either you'll add more history pods so that you then sort of even out the shards again, across more processes than they were before, or you can just up the history limits. But make sure you're always checking CPU, memory, whenever you make any kind of configuration change to Temporal. Matching. So we're getting to the point where you're sort of getting to where you're going to remove the big bottlenecks from temporal server, I would say at this point. There's like the last 20% of performance from self-hosted is normally sort of tuning the workers. But like when you've got history and matching sort of properly tuned, you've got like 80% of the performance normally. Matching is a lot simpler than history. It's basically, if you're using too much CPU on each process, you spread you add another process so that it spreads the work out more. There is something called task queue partitions, which is it's like the matching equivalent of history shards, but it's unlikely that you need more task queue partitions unless you've sort of really hit a huge scale, and you'd probably know by that point that that was an issue. So I'm not going to talk about it here because it's too complex. But just to mention, that's the equivalent of shards for matching. And then the last thing is scaling polling. So this bit applies to temporal cloud, whereas the rest was all self-hosted only. So task queues are basically a buffer between your workers and matching. So whenever there's work available to do that temporal has decided needs doing because your workflow has asked for it, it's going to sit in the task queue. Now, ideally, we want to be holding that entirely in memory. It's called sync matching. So your worker is going to say, hey, I've got some time, I can do some work for you. And matching is going to throw it a task out of this buffer that's in memory. And that's really quick because we don't need to touch persistence to do that. If, however, your workers aren't pulling work off the buffer quickly enough, it's going to build a backlog, and then we're going to have to start running out of room we will start running out of room in memory. We're going to have to start persisting it and reading it back, and that slows things down a lot. So there is a metric, which I noticed very happily was in the Datadog dashboard, sort of front and center. Give that a go. Was poll sync rate, and that's a measure of how many of the poll requests were served from memory versus how many had to go through disk. So you want to get that to 1, as Tio mentioned, which normally involves adjusting the poll accounts on your workers. The defaults are really quite low, so definitely experiment with that. You're looking to make sure that you are sort of setting them so that you don't exhaust the execution slots on the worker, which is all included in the documentation about how to figure that out. But you really want to adjust the poll accounts to make sure that your poll sync rate for every task queue that sort of has reasonable throughput is approaching 1, which means that everything is being served synchronously rather than asynchronously. A couple of other metrics to mention, which are kind of SLO things. If your polling rate is if your poll account is really low and you're not pulling tasks off the buffer quickly enough, then by virtue of that, your latency is going to be higher because your worker isn't able to receive the work quickly enough after temporal decides that it needs to be done. So that's where your scheduled to start latencies and activity scheduled to start latencies start to creep up. So the solution is that to add more workers or to increase the poll account. So we can see an example here. Poll sync rate is like 95%, and our scheduled to start latency is higher than we want. It's out of our SLO. And then we add more workers, we increase the poll count. All these images are from the blog post, by the way, which is linked to, so you can follow the full story there. Poll sync rate jumps up, and we can see that our SLO is like flatlined on 50 milliseconds, which is way under our target. So that's kind of the impact you can expect from that. Okay, I made it. Whew. In summary, make sure you run through your talk a few more times before you give it so that you don't end up with pacing issues. Performance test runs, load measure scale is a really useful methodology for doing these kind of things, in my opinion. Always run it multiple times. A great example of that is the fact that I mentioned history pods and task queue partitions will not balance evenly. Different processes will get different numbers of those things, which means that you're not going to get exactly the same behavior every time. Test for directionality, repeat the tests. Make it easy to repeat them so that you don't accidentally forget to wipe persistence or anything like that. Measurements. Results should either be state transitions if you're testing how hard you can push the cluster, or application relevant metrics if you're testing a specific workload. How many workflows could I get through in a minute? Whatever is useful for you. Drill into the service specific metrics only when you need to find bottlenecks. Always check CPU, memory, that kind of thing. The sort of the basic processor level stuff. Scaling, add processes or cores to spread the work across CPU. We're a CPU heavy platform with the exception of history, which uses a lot of memory. Watch out for CPU throttling, and again, you cannot currently change the shard count on a cluster. Once you've built it, that's your shard count. It may be a bottleneck later, be careful with it. There are increasingly ways to sort of migrate stuff over. We've heard a lot about global namespaces and cross-region replication and that kind of stuff, but that's not a straightforward thing to do at the moment. So don't rely on that. Performance test, emulate your workloads, and sort of try and get a feel for your shard count before the fact.
Woo, that was good.